so I'm keeping up with what he does. Um, so I don't have access to the chat or to the comments. So if anyone has a comment or a question, please go ahead and unmute yourself and go ahead and ask me and stop me. Okay, if I'm going too fast or too slow, let me know. Let me know how I'm doing. Okay, so let's get started. So for today's topic, again, we're doing Math 1324. And topics for today are sets, probabilities, permutations, and combinations. Okay, so these are the topics for today. So let's go ahead and get started. So the first thing we want to do is we want to have the definition of what a set is. So your book defines sets as a well-defined collection of objects. Okay, now these objects can be basically anything that we want to do math with. So examples of sets that are well-defined would be these examples. All the students in my math class. Okay, it's a well-designed, well-defined collection because it's specific. I'm not just saying any students. There are students in my math class. Or that second example, letters in the alphabet. We know that in the alphabet there's 26 letters, so this is a well-defined collection of objects. We know what they are. Okay, we can name them. Okay, so this is what examples of objects can be. And again, they can be practically anything, but it has to be well defined. Okay, so a not well defined set would be saying the collection of young adults. Well, what type of young adults? What age group are we talking about? Who's young adults? There's a lot of questions that we can ask about what young adults are we talking about. So this is why it's not a well defined set. We don't know what young adults we're talking about. Yes. So that's what a set is. It can basically be anything that can be well defined. Okay. So um, to make this one, if I wanted to make this one as a set, I would have to change it. The collection of young adults between the ages of 18 and 29. Oh, now this is a well-defined set. Yes, because I'm looking at, oh, the young adults, I'm looking at the ages between 18 and 29. Okay, so very easy to make sets of ordinary things. Okay, so the next thing we need to know is that when we're dealing with sets, okay, we're going to give them names. Okay, so that way we can distinguish one set from another. Okay, so the convention is for names, just like our names, we capitalize our names. Well, we are going to capitalize the names that we give to sets. The most common letters that we use for the names of sets are going to be these A, B, and C. These are the most common. Sometimes we might throw a D and an E, but you'll just see A, B, and C. Okay, and again, they're capitalized. Okay, now each object in a set is called a member or an element of the set. And for me, when I'm doing my presentation, I'm more familiar with the name element. So you're gonna hear me say more the word element than member. Okay, but what that just means is these are the objects in the set. So for instance, if I go back to um, like the young adults, an element in that set would be, a young adult of 18 years old or a young adult of 20 years old. Okay, it's an element in the set or again a member, but you'll hear me say more element than member. Okay. Now, when we're putting elements in our set, okay, we're going to use our squiggly brackets. Okay, these are our braces. These are used to enclose our objects in a set. Okay, so an example, I have a set here. The name is A, capital letter A, and I'm using my squiggly bracket or the braces. And my set has three elements, 3, 4, and 5. Okay, these are my elements in the set. So again, just what I said, this is set A that consists of elements 3, 4, and 5. Okay, um, we have this symbol. Symbol E is represented in the syntax for sets, and it signifies an element in the set. So let me give you an example how we use the symbol, um, this Greek symbol. Okay, but let me use the opposite of this. If I slash a line through this E looking symbol. It looks like an E. It's not an E, okay? But it looks like an E, right? If I do a slash through this symbol, okay, this means that it's not an element in the set. And we're going to be using these symbols to answer some of our homework questions and some of my example questions. Okay. So for instance, going back to this set A, I have these three elements. Okay. The way I can describe this set A is two ways. I can say I have 3 is an element in A, yes, in set A. Or I can say 3 is an element in the set 3, 4, and 5 because it's true, right? 3, 4, and 5 is basically all of the elements that are in A. Okay, so these are two ways to use this symbol. Okay, that means an element in the set or of the set. Okay, so let me hide this because it's in the way. There we go. 3 is an element of set A, or 3 is an element of the set containing 3, 4, and 5. Okay, so this is how we use this symbol. So to use the slash, not an element of the set, for instance, 2 is not an element in A, and we can see that. We don't in my set A, I only have three elements, 3, 4, and 5. 2 is not part of that. Or I could say 2 is not an element in my 3, 4, or 5. Right? So again, this is how we read it. 2 is not an element of set A, or 2 is not an element of the set containing 3, 4, and 5. Okay. Again, any questions, please feel free to unmute yourself and ask me. Okay? So let's look at more set definitions and examples. Okay, so first, an empty set. An empty set, yes, go ahead. Okay, an empty set is a set with no element. Okay, one way we can represent the empty set is with these two symbols, either a zero with a slash or just the squiggly bracket or braces with nothing in there. Both of these two symbols indicate that we are dealing with an empty set, meaning no elements. Okay. An equal set. Another definition, an equal set is a set containing exactly the same elements. So let's look at an example. For instance, if I have these two sets, 3, 4, and 5 is equal to 5, 4, and 3. Okay, the order doesn't matter in the sets. As long as I have the numbers in there or the elements in there, the order doesn't matter. So all these three sets that I have here are all equal to each other. Why? Because they all have three elements and all three elements are the same in all three sets. This is what makes two sets equal. They have to have the same number of elements and they have to have the same elements, the same objects inside. Yes? Okay. So sometimes we describe a set by a common property. Okay. And what we use is the explanations that I've been using here is something called the list method. If you see here, my sets is just a list of elements. I have 3, 4, and 5. They're all separated by a comma. So we call this representation of sets the list method. But there's another way we can express sets, and this is used by um, applying what's called the set builder notation. So let me go over the set builder notation. This is the syntax. This is how we write in set builder notation. We're still going to use the squiggly brackets, okay, or the braces, okay? And the way we read this is here. We have X, and then we have this line. We call this a pipe, and we read this like this. The set of all elements X such that, and that's what the line means here. The pipe, just like the line here that's separating the two X's, such that X has the property of P, okay? And what this means is it represents all elements of X having some property of B. Okay, so let's look at this example here. So X such that X has a property of P. So this is a set X, okay? All of the elements of X are represented here, okay? Such that is, again, my pipe symbol here. And then X has a property of P. This is X has a property of P. Is what I'm describing my set X to be of. Okay. This format is called a set builder notation. You see, it's not a list. It's giving a definition or a representation of what I'm looking at. Okay. So let's look at some examples. Okay, that are in set builder notation. X such that X is a natural number more than 5 and less than 8. Well, let's represent this as a list, okay? X is a natural number more than 5, okay? So if I just said that, I would be looking at the numbers 6, 7, 8, 9 until forever. But it says there's another condition, and my natural number has to be less than 8. So that means that is between 5 and 8, but not including 5 and 8. So what are those two numbers between 5 and 8, not including 5 and 8? Which would be 6 and 7. Yes? So what if we look at the second example? Okay? So x such that x is an integer and this integer is greater than -3, but less than or equal to 1. This is how I would read this problem. Okay, so this is in set builder notation. So I'm finding an integer that is greater than -3, but less than or equal to 1. Well, what are those values or elements in my set? So greater than -3 would be -2, -1, 0, and I would stop at 1 because my x value has to be less than or equal to 1. So as a list, this is how I would represent this set: -2, -1, 0, and 1. Again, and we'll use both of these methods in your homework. Sometimes they'll give them to you in set builder notation, or sometimes they'll give it to you as a list. Okay? So need to know, it's very important, need to know how to do both of these, forwards and backwards. Okay. Now, other things to know that help you rule review that you also need to know is this definition of what whole numbers are, what counting numbers are, and what the natural numbers are, or the counting numbers. Okay, so again, whole numbers are 0, 1, 2, 3. On counting numbers don't include 0, they're just the 1, 2, 3, 4, and forever. They're the positive values. Yes? All right. So let's look at these homework problems. It says state whether the statement is true or false. So the first one says 3 is an element of 2, 5, 7, 9, and 10. Is this a true statement or a false statement? Well, do you see 3 in that set? No. So then this would be a false statement because 3 is not included in that set, or it's not part of the elements in that set. Okay? What about number 2? Is 2 an element of that set? Yeah, you see that 2 is in that set, so this is a true statement. Yes? So here on number 2, going ahead of myself, um, 2 is an element of the set. Again, the previous one, 3 is not an element of the set. Okay, what about number 3? 3 says 6 is not an element in this set. Oh, this one is a true statement because 6 is not an element in that set. How about number 4? 4 is not an element of 2, 4, 6, 8. This is a false statement because the set does have that element 4. So this would be false because 4 is an element of the set. Okay. How about 5? Um, I have a list only 1, 2, 3, 4. Is this equal to 4, 2, 3, 1? The answer is yes, because both sets have 4 elements and both sets have the same elements. They both have the 1, 2, 3, 4. The other one just is in different order, but they're all there. So this is the true statement because both sets have the same elements. Okay. What about 6? ABC is equal to ABCD. Oh, this one's not a true statement because uh, I don't have the same number of elements. One has one more than the other. Even though I do have some, one has one more, so this is not the same since I have one less or I have one more, however you want to look at it, right? Okay, how about number 7? Okay, it says all the whole numbers greater than 5 and less than 9. Okay, So if I'm just looking at the words on this left-hand side of this equation, says greater than 5. Greater than 5 would be 6 and up. Less than 9 would be less than 9, not including 9. So then this one is a true statement, right? Because the numbers greater than 5 and less than 9 are only 6, 7, and 8. Okay, how about number 8? All natural numbers not greater than 4. Okay, so what do we think? So this is a false statement because it says all natural numbers not greater than 4. Why is it just a false statement? Because it's including the 0. Okay, so natural numbers do not include 0. So this would be a false statement. Take away the 0, then it would have been a true statement. Okay, how about number 9? X, now this one's in set builder notation. X such that X is an even integer. So the element has to be even integer, but also there's another condition. This even integer has to be greater than or equal to 5, but less than or equal to 19. Okay? So what are my even integers greater than or equal to 5? Well, we have 6, 8, 10, 12, so on and so forth, but less than or equal to 19. So my end caps are at um, 18, right? So even integers, so we will have 6, 8, 10, 12, 14, 16. I think we're missing one. We're missing 18. So then would this be a true statement or a false statement? This is a false because we're missing one. We're missing the 18. I was like, wait, there's an error, but they're asking us true or false, right? So we're missing the 18. Okay. Again, if you send me a message, I don't see them. I heard the click for the message. So if you have a question, please just unmute yourself and let me know because I can't view the messages or the screen, okay? I'm sharing my screen. So if you have a question, please feel free to just unmute and ask, okay? All right, now the last one. X such that X is a vowel. Oh, my vowels are A, E, O, U, right? A, E, I, O, U. I know I'm in Spanish. So is this a true statement? Yes, because the vowels are A, E, I, O, U. Okay, these are the vowels as listed. Excellent. Any questions? All right, now let's go into another topic dealing with sets. We are going to look now at subsets and proper sets. Okay, so first let's get some definitions, some terminology out of the way. When we're dealing with something called the universal set is basically the set that contains all the objects being discussed. That means everything, okay? So if I'm looking at, example, if I was looking at the set of the alphabet, okay, my universal set is 26 elements. It's all the letters in the alphabet, A, B, C, all the way up to Z. Okay, that's what a universal set is. All the elements that contain or objects that are discussed. Okay. Now, subsets and proper sets. Okay. This is the book definition. A set A is a subset of set B, and this is how we write it. We write it. It looks like a C with an underscore. And what this means is that every element in A is also an element of B. This is what a subset means. That every element in A is also an element in B. Now, a proper subset, okay, the book definition says a set A is a proper subset of set B, and we write it without the underscore. So it's A with a little CB. And what this means, for it to be a proper set, excuse me, means that every element in A is an element in B, but B contains at least one element that is not a member of A. Okay, this is what a proper subset is. That B is going to have one more guy that is not in A, one more element that is not in A. Okay, so when A contains an element that is not in B, then A is not a subset of B, and we write this as the slash. A is not a subset of B. Okay, and this is we're talking about A. When A has one more than B, we can have one more in B. That's a proper subset. But if we have one more in A, then it's not a subset at all. Okay. All right. several things also to consider. Okay, the empty set. Okay, remember if you see the little zero with a slash, that means empty set. All empty sets are proper subsets of A. Okay, and then the empty set is also a proper subset of A. All empty sets, because all empty sets are included in all sets. Okay, one thing you should know. And of course, if we're dealing with the same set, all sets are um, subsets of each other, okay, or of them themselves. Okay, let's look at these examples. Better get them. Okay, so let's look at this. I have three sets here. I have A, B, and C. A has elements A, B, C. Set B has elements A, B, C, D, and I have set C are C, A, B. Okay, so um, let's look at this. Um, A, it says, is a subset of B? So for this means every element in A is also on B. Oh, okay. So B, B says A is a proper subset of B. And this is true because every element in A is an element in B, but B contains at least one element not in A. In this case, it would be D. Okay. C says B is not a proper subset of A. The reason for this is it says every element in B is not in A. Okay. D. D says A is a subset of C. This is true because every element in A is also in C. E. A is not a proper subset of C. And this is true because A is not a proper set of C because A is not equal to C. Okay? And then the last one, the empty set is a proper subset of A. And this is true because the empty set is a subset and proper subset of any set. Okay? Don't forget, keep this in mind. The empty set is in all sets, and all subsets and proper subsets. Okay? All right, let's do a more interesting problem. Okay, now let's solve this. It says we have, again, now we have several sets. We have A, B, C, D, E, and U. Remember, U is the universal set. U is telling me these are all of the elements that I'm being considered. So that last one, U, is my universe. But I do have just individual sets. I have A, B, C, and D, and E. Okay, so it says insert a, a subset or, I'm sorry, insert a proper set or a not subset to make the given statements a true statement. Okay, so let's look at this. We have 11 through 19. So A and the universe. So for this one, A is a proper subset of U. Why? Because every element in A is an element in U, but U contains at least one more element that's not in A. Okay? So hopefully you're getting this super easy stuff, right? How about E and A? So E and A is also a proper subset of A. Why? Because every element in A is an element in A, excuse me, every element in E is an element in A, but A contains at least one element that's not in E. Yes? So again, I'm just going through this because I think we can see them. But again, let's just review this number 12 so you can see it. So set A is just the negative 4. And I'm comparing it with my set A. My set A has negative 4, 0, and 4. So negative 4 is in there. But A has one more, at least one more than E, right? It has two. It has a 0 and a 4, and that's okay. It just has to have at least one more, and that makes it a proper subset. Okay, so if I continue going on, what is A with E? Again, A is just three elements, negative 4, 0, 4, and E is just one element, negative 4. Oh, this answer is not a uh, not a subset, because I'm going with A has more elements than E. Yes? So that's why it's not. Okay. How about 14? B and C. B, I have the elements -3, -2, -1, 0, 1, 2, 3, and I have C -4, -1, 0, 4. Okay, again, this is the same thing. My set B has more elements than the C that I, or the set that I'm comparing, so it's not um, a subset. Okay. Oh, this one should be easy. The empty set with A. Okay. So the empty set with A, we know that this is a proper set. The empty set is a proper set and a subset for all sets. Okay. This is a freebie. Okay. I hope. Um, how about this one? The set or the element 0, 1 with D. So D has 0. So this one is neither, right? Because the first element has one more than D. Has only one element, and I'm comparing it with something that has two, so it's not a subset, excuse me. How about 17? D and 0, 1, the other way. Oh, this one is um, a proper subset because D is only 1, is 0, and the set that I'm comparing it with has a 0, so it's there, and it has at least one more, which is the 1. So then this one is um, a, a proper subset. Yes? 18. D and B. Okay, D is just 0, and B is -3, -2, -1, 0, 1, 2, 3. So 0 is in there. So yes, it's a proper subset because it has at least one more. It has a whole bunch more, but that 0 is there with one additional one more. Okay. How about A and C? Okay, A is -4, 0, 4, and C is -4, -1, 0, and 4. Okay, this one again, it is a proper subset because C has at least one more element that's not in A. Okay, all right. Again, if you have any questions, please just unmute yourself and let me know. Okay, all right. Dealing with more with subsets. It says list all the possible subsets for each of the given sets. Okay, so all of the possible subsets. Okay, recall what a subset is. A subset is um, all the elements that are of A that are also in element B. Okay, so for instance, my solution, say for this two elements, 4 and 6. So all of the subsets for this would be, again, not the empty set. The empty set is in all sets, okay? But I also have 4. 4 is um, an element that's in 4 and 6. And then I also have 6. 6 is also an element that is a subset of 4 and 6. And we cannot forget 4 and 6. 4 and 6 is a subset of 4 and 6. Okay, so these are all our subsets for 4 and 6. It would be the empty set, the 4 by itself, the 6 by itself, and the 4, 6. Okay, so these are all of them. Okay, all right. What about B? Um, so a set with two elements has 4 subsets. Okay, all right. And I'll show you the formula for this. Okay, Um, so for the solution for B, I have A, B, and C. I have 3 elements. I'm going to do the same thing. But the most common one that my students forget all the time is the empty set. Okay, start off with that one always. The empty set is a proper set and a subset of all sets. Okay, so the empty set is a subset set of A, B, C. Okay, then let's just break them down. The A by itself, the B by itself, the C by itself, but then I can do groups. I can do AB, I can do AC, I can do BC, and then I can do finally all three, ABC. So again, um, these are all the subsets for the given set. Okay, so what are they? List them. The empty set A, B, C, A, B, A, C, B, C, A, B, C. These are all my combinations. Now, we don't put duplicates because, again, the order that's inside the sets doesn't matter. So A, B, and B, A would be the same thing. So I don't write that order because as long as the element is in there, The order does not matter. Okay, keep that in mind. Okay, so a set with 3 elements has a subset of 8 elements. Now, how do I do this? Okay, the formula to find out for you to check to make sure you haven't forgotten one is to find how many subsets a set should have. You would use this formula. A set of n distinct element has 2 to the n subsets. So for instance, the first one, I have 2 elements. So 2 to the 2 is 4. So 2 to the second power is 4. Okay. Or the part B, I have 3 elements in the set. So 2 to the third power is 8. 2 times 2 is 4. 4 times 2 is 8. Okay. So this is a way for you to double check that you haven't forgotten a subset. Okay, oops. All right, now let's look at these examples. Find the number of subsets for the given sets. They're not asking me to list them. They just want me to find out how many I have. So here, have 1 element. So this would be 2 to the 1. So my answer would be 2 subsets. Now I know this one would be easy. If you don't see it, um, we have 3. What's the other one? The empty set. Don't forget the empty set. It's always forgotten. Okay. Even though it's not there, it's the empty set is I can have nothing in there. Okay. All right. How about 21? Red, white, and blue. Oh, this is just 3 elements. So this is like problem B, right? So it's 2 to the 3, which would be 8. How about 2? Ooh, 22. That's in set builder notation. So we have x such that x is a whole number less than 5. Okay, so a whole number, we're looking at the 1, 2, 3, 4, but it has to be less than 5. So again, these are and 0. So we have 0, 1, 2, 3, 4. So we have 5 elements. So this would be 2 to the 5, which would give me 32 subsets. Okay, so 32 subsets would be included in this set. Now let's do something more with these sets. So we can do operations on sets. Okay, and the way I like to talk about this is sometimes we'll be doing the opposite of the set, or we're going to be adding or subtracting sets. But you'll see what I mean. So first, let's get some definitions. Okay, so if we are given a set A and the universal set U, the set of elements in U that do not belong in A is called the complement. Okay, and the way we write the complement is we do little hyphen to the set. So, for instance, if I'm looking at um, A, its complement is written as A with a little hyphen or a superscript. Okay, we call this a prime. So we would read it as A prime, or we can just say not A because that's what it is. The complement is the elements that are not in that element. Okay, so let's look at an example. It says, let the universal set be 1 through 12. We have all these numbers. And if I have set A is equal to 1, 2, 3, 4. Okay. All right. This is kind of an introduction to Venn diagrams. When we're doing Venn diagrams and we're dealing with sets, we represent a Venn diagram as a box. Okay. The box, inside the box, is going to represent my universe. So in my universe or inside this box, I'm going to have all these numbers 1, 2, 3, 4, 5 inside here. The way we represent objects in using Venn diagrams or our sets, we use circles for our objects. So here, my universe is these guys, and I have one set or one object, which is A, and I represent that as a circle. So inside this circle, okay, which is A, I have these elements, 1, 2, 3, 4. Um, the to demonstrate the complement of A is everything that's outside this circle. Okay, so everything that's outside the circle would be the complement of A. And we like to use Venn diagrams because the Venn diagrams are a way for us to see pictures of the math without having to count. The picture will tell us, you know, a million words, right? So it says find the complement of A or find not A. So if I use my Venn diagram, I would put all of the elements that are in A. Okay, so my elements in A are 1, 2, 3, and 4. All those numbers would be inside my circle, the 1, 2, 3, 4. So the complement of A would be all the elements in my universe, but not 1, 2, 3, 4. So it would be very easy to see that the complement of A would be just 5, 6, 7, 8, 9, 10, 11, and 12. That is my complement, okay? Not the elements in A, okay? So again, if I were to draw them out, okay, normally since I was just talking about it, I put the A inside the circle, but the name, usually we put that on the outside. But since I know what we're talking about, all my elements in A are these 1, 2, 3, 4. And now it doesn't matter where you put them as long as that they're inside the circle. Now, my universe is made out of 1 through 12, right? So all these other numbers, I can put them anywhere inside my rectangle, okay? This is my universe. These are all my numbers. And here, like I said, it's very easy to see the picture. The complement of A is everything that's outside the circle. Okay. All right. So let's look at the AND operation. Okay. So the AND operation is also called the intersection of two sets. Okay. So whenever you're given two sets and they want you to find the intersection between the two sets, the symbol representation for that is like a upside down U. Okay, so A intersection B is in this format, and what this means is that all the elements belonging to both sets is what they all share. That's what the intersection means. Is what both sets share. Okay, so um, what another way you can say it is what they have in common. So let's look at an example again. Let's say that I have my universe 1 through 12. I have a set A, which is 1, 2, 3, 4, and I have a set B, which is 2, 4, 6, 8. Okay, so I want this. I want to find the intersection between A and B, what they have in common. Okay, so for instance, if I see here, if I look at set A, um, set A has a 1 but it's not in B. But I have a 2 that's also in B. So those two are in common. I have a 3 in A but not in B. I have a 4 in A. Oh, that's also 4 in B. So these are the two elements that I have in common between the two sets. So the intersection of A and B would be just 2 and 4. Okay. Now let's see. Let's let me show you how I represent this using Venn diagrams. Okay, so again, a universe is represented by my box. Okay, my universe has two objects now. I have A and B, so I have two circles, and I know that I put them overlapping each other. And I like to tell my students, hey, I have the Mastercard symbol, right? For those of you who have that credit card, it's the Mastercard symbol. Anyway, um, so again, this object is A. This one would be B. So when they're asking the intersection is this part here where they overlap each other. This is the representation of my intersection. Okay, so let's do it using Venn diagrams. We saw it visually, but let's do a picture of this representation. Okay, so my universe has these two objects. So let's start with A. A is on the one on the left. So um, I know that the objects that are shared in both are 2 and 4. That's where these go. So what is only in A? Well, in A is the 1 and the 3. What is only in B? Just the 6 and the 8. Now again, I'm getting you ready for Venn diagrams. I haven't fully talked about Venn diagrams, but this is how we would draw a Venn diagram. We will write the name outside the circle. We wouldn't put it inside. I was putting them inside just for explanation purposes, but when we're actually putting in the elements now, we put the name outside. Now, in convention, we like to put the name on the top of the circle. So anywhere on top of the circle is the name, and all of the elements are inside. And if you see here, if they just gave me the picture of this two objects, it would be very easy to see that, A is 1, 2, 3, 4. B is 2, 4, 6, 8, and the elements that are shared in both is this middle part, the 2 and 4. Or if I asked you, what are the elements in A that are not in B, or would be 1 and 3? Or what are the elements in B that are not in A? Well, it's really easy to see that it's just 6 and 8, right? So again, our universe, though, we haven't finished. I want to finish my Venn diagram completely. These were just these two objects, but I have a universe that's dealing with 1 through 12. So all of the numbers that are not in A or not in B would go outside those circles. And it doesn't matter where you put them, okay? They would all be out here, okay? All right. Um, Disjoint sets. What is a disjoint set? So your book describes as a disjoint set as any set um, where A and C are disjoint, meaning that the intersection of the two sets is the empty sets. So, in other words, if I'm looking at two sets, a disjoint set means that they have nothing in common. Okay, they don't share, they don't overlap. Okay, that's what this means. So let's look at an example of this. If you have my universe, I have a set A, a set B, and a set C. So let's let's practice first our intersection again. What is the intersection of A and C? What does A and C have in common? All right, so let's see here. A is 1, 2, 3, 4. C is 5, 6, 7, 9, 11. They have nothing in common. So what would be the answer for this intersection? The empty set. Nothing, this symbol, okay? All right, so let me represent this scenario here. Okay, we have our universe. This is set A. This is set C. You can see using our Venn diagrams, I see that this answer would be nothing because these two circles are not overlapping each other. Okay, so if I were to write it, okay, again, this is my set A. Okay, my set A contains 1, 2, 3, 4. My other object C is 5, 7, 9, 11. Okay, and if I see they have nothing in common. They don't share anything, okay? And if I would finish my Venn diagram, all the other elements that are in my universe just would go outside these two circles. Oops, okay? They would go outside, okay? All right. So now let's take up the union, okay, or the addition of two sets, or in words, the or, okay? So when we're looking at A or B, whenever you see this word A or B, we're talking about the union. And the way we talk unions is now it's like a right side U. The intersection was like an upside down U. The union is a right side up U, okay? So this is how we read this, A union B, or a or B. So what this means is all the elements that are in both sets, but that do not repeat. Okay, that means all of them. So let me give you an example. Okay, if I want to find A or B, okay, let me write this out. So A is 1, 2, 3, 4, and B is 2, 4, 6, 8. But 2 is already there, so I don't write the duplicate. 4 is already there, so I don't write the duplicate. So the only thing that I'm missing that is all of them is the 6 and the 8. So A union B, or A or B, means that I'm listing all of the elements that are in both sets and I do not repeat. Please do not repeat it or they'll mark them wrong. Okay, do not put a double 2 and do not put a double 4. Okay, all right, let's visually see this. Okay, so if I have my universe, I have two sets. I have A and B, and I know that they share um, the 2 and 4, just like before. Okay, um, this is my universe. I'm finding the or. Okay, A is this 1, 2, 3, 4, and again, they share the 2 and 4 that we had solved before. Element B has the 6, 8. Okay, so the union of those two are all of these values that you see here. Okay, again, to finish my Venn diagram completely, my universe has the 5, 7, 9, 10, 11, and 12 that are outside these two objects, outside my two circles. Okay, all right, so when we're dealing with sets, okay, um, we sometimes want to find the complement, which we already defined. So let's just do an example, okay? So the complement of A is in set builder notation, okay, is X such that X is not an element in A and X is an element in the universe. Okay, this is in set builder notation another form to write the complement. Okay, so visually, this is how you would see it. Okay, the complement of A is everything in my universe, everything in my rectangular box, except with what's inside my circle A. Okay, so the intersection of A and B. Another way of visualizing this, okay, or writing it first, is in set builder notation, X such that X is an element in A and X is an element in B. Okay, it's in both. Okay, how we see this visually is the highlighted section is where these two overlap. Okay, how about the union of A and B? In set builder notation, the union of A and B is where X such that X is an element in A or X is an element in B or in both, right? This is how we will write it visually. It's everything in A and everything in B, but again, we do not write the duplicates, okay? It's all the highlighted section. Okay. All right, so let's do some more exercises. I think we have time. Oh yeah, we have 10 more minutes. We have time. Okay, so let's answer these. Okay, um, we have the set, we have our universe, and we have three sets, three objects, X, Y, and Z. Okay, so the first one says, I want to find X with the intersection of Y. What that means is what is shared in both X and Y objects. Okay, so let's write X. X is this. The just to get ready, let's get this information. So I'm gonna write the complement of X. I'm gonna write Y and get the complement of. Since I have to find the complements, let me just do some scratch work or some ready work so I can answer them. Okay. So Z is this, the complement. I didn't need the complement of Z, so I'm not going to do it. So let's do the first one. The intersection of X and Y. So what do they both share? So here, X has a B, so does Y. Okay. X has a 1, so does Y. X has a 3, so does Y. And that's it. So the intersection between X and Y is just the B, 1, and 3. These are the only elements that they share. These are where they overlap. Okay. What about the union? The unions are easy. The way I do the unions is I start with the X. I write all of the ones in X. So X is A, B, 1, 2, 3. And then I start adding the ones from Y, but not the duplicates. So Y that's not already written there has the D and has the 5. Yeah, so this is the union of X union Y. Okay, how about 25? The complement of X. Oh, I did it in my scratch work. It's everything that's not in X. So everything that's this is excuse me, this is the complement. Okay, so but um, now the next one, 26. The complement of X with the intersection of the complement of Y. All right, so let's look at the complements. I have my scratch work out here. So I have C, D, E, 4, and 5. I want to know what's the only thing that's being shared with the complement of Y, which is A, C, E, 2, and 4. So the only thing that they share we can see is the C, the E, and the 4. So that would be my answer. The C, the E, and the 4 is what they share. So this would be the intersection of these two complements. Okay. What about 27? The complement of X, which would be C, D, E, 4, and 5, with the intersection of Z. This is, again, only thing that they share. Okay. So when I see here that the only thing, they don't share anything. So this would be the empty set, right? So this is the other way of writing it, the two squiggly brackets with nothing in there, okay? Or you can write the 0 with the slash. Both of them mean the same thing, okay? Or this one. All right. Now, the last one is a little tricky because we have to follow order of operations. Oops, we have a parentheses. Yes, so we have to do that first. Okay, so um, when I'm looking at this, I'm going to do x with the union of that parentheses first, the intersection of y and z. So that means that I want to share, I want to do the union of x, but with only thing that is shared with y and z. So again, if I look at Y, which is BD135, and Z is um, B23, what is it that they share? They share a B and a 3. That's what they share. So that's what I'm comparing this with. The intersection of Y and Z is just the B and the 3. Okay, so how do I write the union? Again, I like the unions because they're easy. So I would write everything in X first. X would be A, B, 1, 2, 3. Now, I would write then what's in the union of B and 3, but I already have B and 3, so I don't write the duplicates. So this is my answer. It's just A, B, 1, 2, 3. Okay. All right. So I think I have time to start introducing more a little bit of Venn diagrams. Okay. So a Venn diagram is a way to represent sets, okay, or objects, and it's a visual way of representing them. So again, review. Uh, in Venn diagrams, we use a rectangle to represent our universe, everything that we're dealing with. The objects in our universe are represented as circles, okay? And where they overlap is our intersections. Yes? So, um, let's look at this again. The universe, we always like to label the universe. We write it on the top. Okay. So if I say that my universe is A, B, C, D, E, F, and G, this is what I'm looking at. Okay. So let's let's draw this the list of the picture that we have. Okay. So my universe, I gathered all of the elements that I see, and these are A through G. Okay. So I can label these. If I label this as object A or my set A, I can list it. A is made out of A, D, E, and G. Okay. If I say that this is my object B is B, D, G, F. Okay. And last, if this is my C, my object C, C is C, E, G, F, G, or C, E, F, G, excuse me. Okay. All right. So let's answer some of these. What would be the intersection of A and B? Just what is overlapping between A and B. And here we can see the picture. And the intersections between A and B is just D and G, right? How about the intersections of A and C? Okay, without having to do anything or circle and find out what's sharing, we can just look at the picture. What is overlapping between A and C? Oh, it's just G and E, right? Or E and G. Okay. Um, what about the intersection of B and C? Between the intersection between B and C is just what's overlapping this center little oval. So that's F and G, right? Okay. Um, what about this one? Um, I want to find the intersection of A with B and C. That's where all three circles overlap each other, and you see that we have one. The answer is just G. Okay. All right. So let's do this word problem that I think we have time for. It says 60 people were contacted to respond to a movie survey. The following information was obtained. Okay, 6 people like comedies, dramas, and science fiction. 13 people like comedies and dramas. 10 people like comedies and science fiction. 11 people like dramas and science fiction. 26 people like comedies. 21 people like dramas. 25 people like science fiction. So we did a survey and we got these responses. So it says A, use a Venn diagram to illustrate the survey's results. Okay, so let's start that. So I know I'm going to use a rectangle because that's how I represent um, Venn diagrams. Okay, I'm going to have a universe. So my universe is all the people that got surveyed. How many people got surveyed? 60 people. So my universe is 60. Now, in these people, their responses, I had three responses. I had comedies, drama, or science fiction. So I have three objects, so I'm going to have three circles. Okay. So when you're doing the Venn diagram, you're always going to work inside out. And what I mean by this is uh, I'm helping you, right? I started with the highlighted in red. I'm going to start with this one. Six people all three. That's the intersection between all of these, right? So again, my universe is 60. Let's label our objects, okay, our circles, okay? So let C be comedies. So let's label that one, C the top one. Let D be dramas. We'll label this one. Let S for science fiction be this one, okay? So these are my three objects and they are labeled. Let me start filling this Venn diagram out. I'm going to start with the inner first, okay? Start with the intersection of all three. I had six people who said that they liked all three. Well, that goes in the center right here. Okay. Now let's start branching out. Okay. Let's start with the intersections. Let's do the intersections between C and D. It said that 13 people like comedies and dramas, but I already have six people there. Again, we don't include duplicates. So what if 13 people like comedies and drama and I'm already looking at six? What's the difference between 13 and six? Well, this is seven. So that goes here. Okay. Um, let's look at another intersection, the intersection between comedies and science fiction. There is 10 people that like comedies and science fiction, but I already including six of those liked all of them. So what is the difference between 10 and 6? 4. That goes there in that little area there. Okay. Then one more intersection to go, drama and science fiction. It says that 11 people like drama and science fiction, but I already have six that like drama and science fiction. So I'm missing five, the difference from 11 and six, which is five. Okay. So now I can continue working outwards. I can finalize all my objects. Okay. Let's start with C. C, there was 26 people that like comedy. But in my circle C, if you see here, inside the circle, I already have 4, 6, and 7. 4 plus 6 is 10, plus 7 is 17. So I already am including 17 people. I don't want to count them twice. Do not do duplicates. So what is the difference between 17 and 26? Well, that is 9, right? So 9 people just like comedies by themselves, okay? And I'm giving some of the answers already for the rest, okay? So unfortunately, I did run out of time, okay? I'll go ahead and stop here. But again, if you want a copy of the presentation, you can find it on our YouTube channel later on. So I'll go ahead and pass it on to our presenters. Thank you so much for joining me today.
Thank you, Mr. Carrizales, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. Today's session will also be available on that playlist later on today. Also linked is a short survey to help us improve our TV sessions. Please take time to fill out the survey. We will be back with Happy Math Hour next week, where the Math 1314 will be covering inverses and determinants of matrices, and Math 1324 will be covering the concepts and probability, permutation, and combinations. Before today at 1 p.m., we will also have the student success topic, which will be EPC Culinary Arts. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or mic. Have a great weekend, everybody.